Well, welcome to Chapter 8. I know we're going a little bit out of order, but I think it makes a little more sense for the way that we are doing things in our class. We're going to talk about soil and the earth and erosion and things like that. You may recognize the picture behind me here. This is the Grand Canyon. Some of you may have been there before. I've been there a couple of times myself. It is more than a mile deep. If you think of how long a mile is in terms of the number of feet, 5,280. This is more than 6,000 feet. In fact, the last measurement I saw was 6,001 feet at its deepest point. And it has been caused by erosion and weathering and other processes that we'll see in our lecture today. But we'll also talk about different things to do with the soil. Let me share the screen here, and we will go to our PowerPoint for Chapter 8, Use Slideshow. There are some of the pages that I will just go through rather quickly. You can read them on your own, including the things that you're supposed to be learning through all of this. This talks about soil formation and rock processes. In our labs, we're looking at rocks and minerals. But this is sort of a base of that. So I thought we would look at this first. There are three main processes to keep in mind. There's weathering, which is what happens on the surface. So rain and snow and ice and other kinds of things changing the way our surface is, often the soil and the dirt and the rocks that are on the surface. That's called weathering. We have mass wasting, which can be sort of like a landslide. That can also be involved in volcanic processes. Usually it has something to do with the gravity pulling things from a higher to a lower elevation. And then we have good old-fashioned erosion. Erosion is something else doing something, like wind, the sort of wind blowing the sand dunes along, water. That's what's caused the Grand Canyon here, and ice. Ice is one of the things that we don't tend to think of as being an eroding process, but it is actually an agent in erosion processes. If we look at the Grand Canyon, we can see where we've had areas of weathering. We can see where we've had some slumps, so that would be mass wasting, and we can see where the river started out. Once upon a time, it was just going through a plain here at the top, and it has eroded things down. And as it eroded things down, things would slide in. At certain points, the Colorado River would be blocked, but it would eventually overflow and then push it through. It's been going for tens of thousands of years through here. And then we can look through and see the weathering that happens on a day-to-day and a year-to-year basis and continues. The Grand Canyon continues to be sliced, so it will simply go on getting deeper and deeper. It will also continue to weather and get wider and wider as the parts that are there will weather away. We can see these kinds of weathering processes happening in our own backyard. This picture could actually be taken in Bloomington, Indiana. I've seen a lot of sidewalks that have been broken up because trees and trees' roots have grown beyond their little area. You sometimes see a little fence as if the fence was going to keep in the tree. So this is what we would call mechanical weathering. One of the more mechanical weatherings that we tend to see is when ice infiltrates itself into the cracks, and ice expands when water expands when it turns into ice, and then when it melts it runs off, but it leaves that crack, and that gets wider and wider. That's a mechanical weathering process as well. Chemical weathering is when something chemically happens to it. That will often happen through acid rain, for example. Impurities in the rain will mix with the rock and it will actually change it into something else. So sometimes we get discoloration as well as changes in the way it's shaped. We can see mechanical weathering in what's called frost wedging. That's what I meant when we get sort of the water that goes in and then breaks things apart as it freezes and then it sort of leaves a gap when it melts. Then the next rainfall comes in and fills it all in again, and it expands even more. Any place like Indiana that has a lot of freezing and melting processes will get a lot of potholes. That's why we get a lot of potholes, especially in the spring. You'll notice them because that's where all of the things that have frozen and melted and frozen and melted, and finally it's all melted and it's not freezing anymore. So you're left with the leftover. We can get sheeting and salt crystal growth. These will also happen in that same process of expanding out. And then we have biological activity, which can happen when a tree grows and its roots begin to separate things out. You wouldn't think that a root of a tree would be harder than rock, would be stronger than rock, but you would be amazed. One of the things that we can keep in mind there is part of what goes into a tree or into biological activity is water. So we've got that happening there as well. We can see in images like this, where we have water coming into the cracks, it freezes and it breaks things apart. And then we have different kinds of slopes that happen from the things that are falling down. But often we have these huge, big crevices within the tops of mountains where things have been wedged apart. We can see sheeting in this process here. One of the things that's happened over time is that rock has been pressed underneath by top soils and top layers of our geological strata. But as that wears away, we are left over with different kinds of things that are left exposed, or sometimes they will be pressed up by processes like the one we have here at Yosemite. There are things that are pressing it up through the topsoil, through the top layers there. And what we begin to see is we begin to see it sort of fracturing and sheeting off as it rises. When we have mechanical weathering, we have a process where we get into smaller and smaller and smaller chunks as water, as small as just a few molecules, can get inside cracks and crevices and then expand. And everywhere there's a crack or a crevice, water will infiltrate itself in. And thus over the process, over time, we have more and more and more chunks of the rock. And each time we have it broken into more and more chunks, we have more and more area that's exposed to water, to air, to other processes. So the mechanical weathering leads to chemical weathering, and they sort of accelerate each way. You wouldn't think, just thinking about it, if you had say here we have 1 cube, here we have in the middle 8 cubes, here we have 64 cubes, you might think, well, they take up the same volume, they take up the same amount of space. But the truth is, as you have this much here, you have twice the number of square units in terms of sides, because you have all these middle sides in here. And by the time we get into this area here, we've got much, much more, because we've got now lots and lots of sides, and those are openings for water and other processes. The most important agent is water. Another important agent is carbon dioxide. Carbon dioxide is leached into the soil, it is leached into rocks, it is leached into various parts of our world as carbonic acid, and that can break things apart along the way. A lot of the carbon dioxide in our atmosphere gets recycled into the soil and into water. So granite, which is something which is a bunch of sort of conglomeration of rocks, and we'll talk a little bit more about this in chapter 2 and 3, as well as you'll have some things in the labs. One of the things that we see is that a lot of the different parts of it will break down, but there are parts of it that will also remain unchanged. Quartz, which is a mineral, remember our minerals lab, quartz will not be too much affected by it, but other parts of it will get affected by it. So silicate minerals, anything with silicon, will end up being part of the weathering process as well. So when we're doing this, we can sometimes have what's called spheroidal weathering. And that's rather funky to come across and see if you sort of look at this in the Joshua Tree National Park in California. We end up with these round rocks, and we wonder, and curved rocks, and wonder how do those actually get up there? How do they stay up there? Did some giant come along and put them up? Well, we can sort of see over time the process. The processes usually don't lead us to a bunch of cubes. What they often do with weathering of many types of rocks is to sort of chip around the corners and the edges. And so we end up with some egg-shaped and some round-shaped boulders. We can see that happening in different things that are not just natural, but also human-made stuff. If you go looking at a grave site, if you go to a cemetery, for example, the older graves look like they're much more weathered. That's what's happening there. The newer ones look much more pristine, but it also depends upon what the tombstone is made of, because some of them will resist the water and resist the carbon dioxide activity and will resist the different kinds of impurities that are in the air and in the rain more than others. People who built things in the past, however, weren't always counting on acid rain from industrial pollutants. That's become a real issue in places like Athens in Greece, because a lot of the materials that went into these 2,000 and 3,000-year-old buildings can't stand up to all of the impurities that are being thrown into the air by the cars that are in the environment, because Athens is a big city with 100,000 cars or more that are all putting out pollutants, and it's mixing with the rainwater. So that's one of the things you might do, is sort of go to a cemetery sometime and look for two different tombstones, say 100 years old, 150 years old, and see if there's differential weathering. And then you'll know, well, that person spent more money on it, that person spent less money on it. We hope, we think, along the way, but things do eventually wear out, even no matter how much money you spend. And then we have interesting things like this that happen. These are really bizarre in many ways. They sort of look like rock mushrooms. But what's happened is these capstones here and here and here are built of sturdier stuff than most of the stuff. This used to sort of be either a hill or may have even been flat land, that most of it got eroded away. But this stuff remains, and the center of this remains. And quite obviously, this hasn't had too many earthquakes in the time that this erosion and weathering has taken place. So as we have this kind of process happening, the stuff that breaks down turns into soil. Soil contains minerals, contains rocky stuff, contains water, contains air. The stuff that's made out of rock and mineral fragments is called regolith. If you follow the probes that we send to asteroids and other planets, quite frequently they are picking up regolith. They're picking up the rocks and minerals and other things that are on the surface of the planet or the surface of the asteroid. These actually help support the growth of plants. So we do need minerals for our own body, so plants tend to need that as well. When we're looking at soil, we can think about it as sort of half and half air and water. We don't tend to think of air as being a crucial component, but in fact it is, for half of the soil. So half of the half is air and half of the half is water. So they're each 25%. The other half is almost all mineral matter. So rocks and minerals. Only about 5% is going to be organic material. Organic material can be carbon stuff. Organic material can also be decomposing stuff. The stuff, the plants and bugs and other things that have died, and they're sort of recycling their organic material back into the soil. So depending upon the texture, how large or small the pieces are, you can sort of think about how large a grain of sand is, and then you can think about how tiny a bit of powder would be compared to a grain of sand. If you hold sand in your hand, you can often sort of see the grains. If you hold powder in your hand, it's just a clump of powder. But that's more like what silt is. And then of course clay, you don't even see it. So usually it's packed together. Then if we have all three of these things, if you go to a greenhouse and buy potting soil or other kinds of things, one of the things that you'll often do is you'll get a loam mixture, and that will have some of all three of these. It can be in different proportions, but loam will have all three of these things mixed together. And this sort of shows you where we have sandy loam and silty loam and clay loam. And then we have just pure loam, which is a sort of a three-way split between the stuff here. But notice that it's going to be a lot less clay when we're in the loamy area. But you'll have a good percentage of sand and a good percentage of silt that's there. So the more clay it is, the less likely it is frequently to let the water through in an easy way, and to let the air through in an easy way. So the salt, or the sand, sorry, and the silt will both let it through much more readily along the way. So we have different soil structures, which often help us determine the water that's getting through it, and whether or not plants can grow in things will depend upon whether water can get through it. So we have platy and spheroidal, which both slow the water, and then we have prismatic and blocky, which are both moderate in terms of letting it go through at a reasonable pace along the way. So these are structures that will help determine what kinds of plants. Different plants grow better or worse in different types of soil. So we have, when we're looking at soil formation, residual soil, stuff that's come from what's there, as well as transported soil. The river brought it there, the wind blew it there, from erosion processes. And time is very important here, because given enough time, the river can wear it away, just like we have at the Grand Canyon. So climate also matters. Whether things freeze and melt will help the soil break apart. We don't have that freezing process happening in the tropics, for example. So down in Venezuela, down in Guatemala, in sub-Saharan Africa, that's not going to happen. Up at the North Pole, up at Iceland, down in Antarctica, in Greenland, for example, we're not going to have too much melting, although with global climate change, we are having more melting and freezing processes that used to be there. And then plants and animals, because plants and animals put organic material into the soil, and they influence the properties that are there. Roots can break things apart, for example. Worms going through the soil can change the physical processes. The things that they leave behind can also alter the chemical processes or properties that are there. So when we talk about this, we're also talking about the topography. Is it flat? Is it at an angle? Is it hilly? Is it a deep valley? Those different things will play into it. We don't tend to have a lot of gardening patches on the sides of the Grand Canyon, for example. When you've got slopes, the tendency will be for wind and rain to wash things away quite frequently. So if you actually want to plant things, having a flat to sort of a moderately hilly area, sort of like what we have in Indiana and the Midwest. Hence, we have a lot of things that are good for growth. Also, the orientation. If you have a slope on something here in Indiana, but the slope is towards the north, usually not as good for growing anything that needs sunlight because the sun is in the south. On the other hand, if you have your slope on the south side and the sun is over there, it's going to get good direct sunlight. There are lots of sensitive plants that need the shaded area, so you'd grow those on the north slope. There are lots of things that need a lot of sunshine. they will be on the southern area. And of course, if you're in the flat land, then you only have to worry about shadows from trees or other kinds of things like that. So here we can sort of see the different kinds of slopes. We can see the farmland is in the flat land here. We have some pasture land up here on the thicker bedrock because we don't have a lot of deep soil for lots of roots to go down into. And we don't do anything on the slopes. There may be the occasional vegetation and trees and bushes and other things, but we don't do a lot of farming on those areas there. As we dig down into things, we have what are called horizons, which are zones and layers. And these are the different layers, O, A, E, B, C. Don't ask me why they're divided into that, except that O actually stands for organic matter, and that's what we tend to have mostly towards the top. The further down we go, the less organic stuff we have, and the more parent material, which is the bedrock that's underneath, coming up along the way. So if we sort of look at this image here, we can see the organic material with the root structure, and then it comes down into the A area, which also has the mineral matter, the sort of rock and mineral matter. Then we have this area here, the E horizon, the zone of eluviation. That basically means we're going to have sort of water leaching through that territory here. Then we have our clay and our parent material, including stuff down here that hasn't broken apart yet, but notice it's breaking apart. If you live in New England in particular, one of the things you get at the end of every winter cycle are Easter eggs, and they're just these rocks, because what will happen is in the freezing and the melting and the freezing and the melting, these rocks will work their way up to the top, and then you sort of go through and get rid of all the rocks that have risen over the course of the previous year, so it won't interfere with your planting. But those are New England Easter eggs. We classify soils according to a particular taxonomy. I'm not going to go too much into that, but you can sort of see here where we have a lot of different types of soil around the world. And as you can sort of guess, look here in the middle of the United States, we have a lot of green area. Those are mollisols. And then we have some of our yellow areas, the altisols. And then we have the lighter green area, alpha sols, sols as in soils. But one of the things that all of these are good for is growing different things. If you think about the South, grows cotton and tobacco and other kinds of things like that historically, whereas we look at the Midwest and we grow soybeans and corn. We look in the sort of middle of the country and we grow lots of corn, but also wheat and other kinds of things which grow all the way up into Canada up here. We can see that we've got different zones that are there. Notice this is similar to this over here in Asia, over here in China, Mongolia, and throughout Russia and the Ukraine. This can explain why there are conflicts in this area, because these are good for agricultural products. We also have some green areas down here. Remember, we have opposites on the northern hemisphere and the southern hemisphere. So where it would be a temperate zone in the north, there's going to be a corresponding temperate zone in the south, but there's not a lot of land along there. So we've got all sorts of different areas on our planet that have different types of soil. Oxysols, look at this here in the Amazon area and in the Congo, Zaire area. These are big, big rainforest areas here. So we don't have many rainforests in North America, certainly not of the sort that we have down here. This is where the equator is. This is the hottest part of the planet. So as we're looking at these kinds of things, soil can actually go from one place to another. And it will sometimes erode by water. It will sometimes erode by wind. There are different ways in which this happens, but it's often a natural process. We can actually accelerate it, but it's a natural process. And it depends a lot on the slope and the climate and whether or not we have the right kinds of things planted. There was a big dust bowl in the United States in the 1930s because so many people went to places like Oklahoma and Kansas, and planted and planted and planted and planted themselves sort of out of all their topsoil. And one of the things that also happened was what trees were there got chopped down so people could have farms, and that kept the wind, or the trees had kept the wind from blowing the topsoil away. And when the trees were gone, it just blew it all away. So there was a push to plant more trees to keep that from happening, which is why quite frequently as you're driving around farmland, you'll see just these sort of weird clumps of trees in different parts. That's intentional. That's intentional. Water erosion is one of the biggest things in our country. 2/3 of all US soil erosion is from water flowing, either rain or lakes or streams or rivers, flowing into usually the Mississippi or other major rivers. More than half of Louisiana, the state of Louisiana, is built up of erosion soils that have just drifted down the Ohio and the Missouri as they intersect into the Mississippi. Wind erosion occurs with dry soil. If it's wet, it's going to be compact and it's not going to blow away. The way we control soil erosion, we can put up our tree windbreaks, as I've mentioned before, like they did in the Dust Bowl in the 1930s, in the Depression era. We can also have grassy waterways that will keep things from flowing away because the roots of the grass will hold on to the soil. We can terrace crop planting. So you can have a level here and then a level here and then a level here, sort of stair stepping, and that keeps it from just washing away. And then of course you can leave the steeper stuff undisturbed and just not plant on those kinds of things here. Here you can see different patterns that are happening in the way that they are planting so that they can have controlled drainage. We have trees for tree breaks in different portions along the way, but they're adjusting what they're planting to the contours of the land to maximize where the water goes in productive ways. We have hay and we have corn sort of interspersed in farmland, and lots of farms will do this kind of thing. So mass movement, as I've mentioned before, gravity takes hold here. Slopes of mountains, of hills, of coastlines, other things change over time. A landslide is one of those things. Frequently landslides are pulled down by gravity, but usually that happens after things have been loosened by water in one way or another, and they can be quite damaging. They can be quite destructive along the way. Sand, for example, is one of the things that will happen to create these kinds of situations, because dry sand, they hold themselves together, but not very strongly. They're holding themselves together by friction. If you've ever gone out to build a sandcastle, you know you want to put a little bit of water in there to pack it in. And over time, it'll dry out and then the sandcastle will blow away again. If you put too much water in it, it won't hold together. So if you've got sandy portions of your soil and you have lots of water, it won't hold together anymore. So that can be a trigger. One of the things we can see is if you build things up of sand or sandy type of material, it may in fact slope down and it will find a new equilibrium. This actually happened in a coal mining accident in Wales. And there was this massive slope that just broke free because the water had infiltrated down into it, and it covered a school and it covered a bunch of other houses and things like that. It was a really major tragedy in the town in Wales. But this is what happens when you have these sort of grains that become unstable. Where gravity will pull it and where it stops is called the angle of repose, because it's now sleeping, reposing along the way. Here we can sort of see unstable slope kinds of structures. Someone unwisely built their house near this. You might think, well, that's a good windbreak, but as water falls from the clouds, it can infiltrate below the soil and pull things down. It doesn't have to be a landslide into the house. It can actually weaken the entire hill structure. So when you're building things like that, you want to make sure that you're actually building on bedrock rather than on a slope itself. Here we can sort of see they've taken away a lot of the vegetation that's here, and that has caused massive landslides to happen. So that's another mass wasting. If you take away too many trees, if you take away too many plants or other kinds of things, that bad things can happen. So we have falls and slides and flows. Those are the primary things that happen with mass movement. Can be debris, mud, earth, rock, all of those things, and it can be fast or slow. There are some that are just sort of slowly slumping over time. And sort of as we sort of see this we have this earth flow that could take years and years and years to occur. And sort of each year you might notice just a little bit more on the road, but you can also then have all of a sudden sort of a big slide depending upon rain or depending upon earthquake activity. Rock slide, you're getting mostly the top level coming down. Again, our road, we don't want to be down here when that happens. And then we have debris flow, which is often what happens when you've got a valley or a culvert or something that can direct the material that's being rained down and pushed by the rain. And then we have just simple earth flows. This is again triggered by water. Water saturates the soil and it becomes liquefied. So it just begins to push out. And these earth flow will tend to be rather slow most of the time. Debris flow will tend to be rapid. Rock slide will tend to be rapid. Slumps can be rapid or they can be slow moving. I've seen some really slow moving slumps out there. Here we have a prehistoric landslide. Notice it says 8 kilometers, so that's about 4 miles from here to here. This is quite a huge thing. All of Bloomington would fit on this plateau. That's a big landslide that's there. Then some of our slower movements are called creeps and solifluxions. Say that 3 times fast, solifluxions. And this also, again, is when we have water saturating things, but there's a frozen surface underneath. So one of the things that this often happens in is the tundra area where we have permanently frozen soils and surfaces. Creep is one of the things that happens when you sort of see the utility pole that used to be straight up and now it's leaning and now it's leaning and now it's leaning. Those kinds of things will happen and cause things to tilt. And at a certain point, of course, things have to be dug up and put back in. But what is happening is we have our regular bedrock and we have a layer on top of the bedrock that's moving a little bit due to expansions and contractions during our freezing and our melting or thawing periods along the way. So things will move and shift very slowly over the seasons along the way. So we can see that also beginning to happen more and more near the Arctic Circle, because we've got permafrost that is not as permanent as it used to be, again, because of global climate change. People built buildings in the 20s and 30s and 40s and anchored their foundations down into the permafrost layer that is no longer permanent. And that's happened in Siberia, that's happened in Alaska, that's happened in Canada, that's happened in a number of places. So we can actually measure that happening. So I think that is it for that portion of our course. I'm going to look very quickly here to see if I think I've covered everything that might be a quiz question. Yeah, remember a couple of different kinds of things that I talked about in terms of buildings in cities, like in Athens in Greece. When we have things made out of marble, like a lot of those buildings in Athens and Rome as well, marble, That was great for the ancient world, but not so great for modern pollution. We have that same issue here in this country with regard to limestone. Limestone will tend to be, I'd say, more responsive, more likely to be damaged by impurities in the rainwater. So that might be something to keep in mind, as I mentioned briefly in the lecture, but I'll emphasize that once again, because that'll be useful for the quiz. So watch for that. So I think that's it for chapter 8, and look for me again. I'll do one lecture on chapters 2 and 3.